Hello guys, this is Wits Lounge, Learning Made Easy. And in today's video, we are going to be considering a very important concept known as amines. Now, before we get into this study, it's important that you like, share, and subscribe to this channel. Thank you. So, having said that, we're going to be considering very important talking points for this study, and they are, first of all, we'll talk about the definition of an amine and get into the classes of amines. Then we'll get into amine as a base and their new structure, basically, and how it affects its basicity. We'll now discuss how to name amines, which is the IUPAC nomenclature, how they are prepared, which is the lab preparation, the physical and the chemical properties of amines. So, as I said, amines are very important organic compounds, generally speaking. You would find amines in the body in form of hormones. You would see them as amino acid. Yes, amino acids are amines. Your epinephrine, your adrenaline, and so much more are referred to as amines. And these are important things, not just to our body, but generally in nature. So, how and what do we describe, or how do we describe an amine? How do we describe an amine? An amine is basically a derivative of ammonia. That's the first thing I would like you to understand. That an amine is simply a derivative of ammonia. It is simply formed by replacing hydrogen atoms in an ammonia structure. So if you consider this as an ammonia structure, an amine is formed when you replace hydrogen atoms in ammonia. So if we are considering the definition, as I said, amines are organic compounds that are formed by replacing hydrogen atoms in ammonia with alkyl or aryl group. Your alkyl groups are basically your straight chain hydrocarbon occurring as substituents, while your aryl group are your aromatic or benzene group occurring as a substituent. Now, having said that, let's look at what we mean by that. Okay, so if you are to have a replacement occurring at this point where an alkyl group represented by R replaces one of these hydrogen, automatically, let's say we have, it's going to become nitrogen attached to hydrogen, hydrogen, and then instead of having hydrogen here, we are going to have an R. Automatically, this is no more ammonia, this is an amine. So this is ammonia, and this is an amine. Okay, so you basically have that amines are formed when the hydrogen atoms in ammonia are replaced, basically. Now, if you noticed, we highlighted something and said that the number of hydrogen atoms replaced in ammonia molecule determines the class of amines. So we'll get into the classes of amines. There are three major classes, and these three major classes are defined or determined by the number of hydrogen atoms replaced in the ammonia. So what are those classes? We have the primary amines, the secondary amines, and the tertiary amines. Let's start with the primary amines. The primary amines are formed when one hydrogen atom is replaced in ammonia by an aryl or an alkyl group. And when that happens, you will find out that the primary amine will be made up of one nitrogen atom attached to one aryl or alkyl group and two hydrogen atoms. So let's get to our board to see what happens here. Okay. So if you consider this particular replacement, only one hydrogen was replaced by an alkyl group, and then we have a particular compound made up of one nitrogen, two hydrogens, and one alkyl. So what do we refer to this as? A primary amine. So when one hydrogen atom is replaced by an alkyl group, automatically you refer to this as a primary amine. Okay, the implication is that a secondary amine would now be formed by further replacement. That is to say, when you replace this another hydrogen by another alkyl group, you get a secondary amine. So let's look at it. You could have NaHR, and instead of having another H here, you find out that another alkyl group replaced the hydrogen. Automatically, what you have here is going to be that this is a secondary amine. And then the final class is the tertiary amine, and the tertiary amine is now formed when the three hydrogen atoms in ammonia is replaced. When the three hydrogen atoms in ammonia is replaced, automatically what you have there is your tertiary amine. So what does that mean? If, for instance, I'm considering this reaction and I replace the three of them, automatically if I replace this other hydrogen, it's going to be N attached to R. Okay, let's use different colors for that. Okay, so we have that the original nitrogen with its lone pair is attached to an arrow here, is attached to a different arrow on this side, and attached to a different arrow on this side. So what we refer to this as is tertiary amines. So you have that. Primary amines are formed when you replace one hydrogen, secondary are formed when you replace two, tertiary are formed when you replace three. So the conclusion is a primary amine has nitrogen attached to two hydrogen. Secondary has nitrogen attached to one, while tertiary has no hydrogen atoms in them. Okay, let's try out some questions to help us understand this. Identify the primary, secondary, and tertiary amines amongst the following. So we have something like CH3 brackets 3N. B, we have CH3 CH2 NH CH3, and then we have C as CH3 NH2. Okay, so which one of them is primary, which one of them is secondary, which one of them is tertiary? It's very simple. As I said, if it is primary amine, it has two hydrogen. Secondary amine, these are like a faster and easier way to identify it, has one hydrogen. And when I mean one hydrogen, I mean one hydrogen attached to two hydrogen. That's in the case of primary amine, two hydrogen attached to nitrogen. Secondary amine has one hydrogen attached to nitrogen. And then tertiary amine has no hydrogen attached to nitrogen. So let's consider that. So if you look at A has no hydrogen, so automatically it's tertiary. A is a tertiary amine. So this is going to be a tertiary amine. We'll get to the nomenclature. This is trimethylamine. Okay. Then we have this. So this is going to be, because it has one hydrogen attached to nitrogen, this is going to be a secondary amine. So this is N-methylethanamine. And then finally, we have that this nitrogen has two hydrogen attached to it. So this is primary amine. And this is methylamine. Okay, so having said this, these are the different ways of identifying your tertiary amines, your secondary amines, and your primary amines. So have that. Primary amines has two hydrogen attached to nitrogen, secondary has one, and tertiary has no hydrogen attached to nitrogen. Okay, having understood the different classes of amines, we are going to consider the basicity of an amine. Now, for us to understand this, we have to first describe or understand what a base is. Now, there are three major definitions of a base, but the most important definition you need to know with respect to this is the Lewis definition. So what is a Lewis base? A Lewis base is any substance that donates an electron. So a Lewis base is an electron pair donor. Electron pair donor. So once you have a substance that has an electron pair to donate, automatically it's a Lewis base. And for us to understand this, we should consider the Lewis structure of nitrogen. Now, the Lewis structure simply means where you have to draw the single electrons, basically, or the electrons in the shells. The first shell of nitrogen contains 2, while the outermost shell contains 5. Now, the important shell that we need is not this first one, it's the outermost shell. In determining or drawing the Lewis structure, what you need is the outermost shell. So, if we're going to represent this as a Lewis structure, we would have this. So, nitrogen on this end can form a bond with hydrogen, can form another bond with hydrogen, can form another bond with hydrogen. So, we would say that in this case, nitrogen has 3 shared pairs and 1 lone pair. This lone pair, or the availability of this lone pair, is what gives this particular substance its basic structure. So it means that any substance that will act as a base must possess a lone pair of electron. You get? So the implication is that something like alcohol is not necessarily a base, but can actually exhibit a basic property because it possesses the lone pair on oxygen. So any compound or substance that has a lone pair of electron actually has the ability to act as a Lewis space. Now, with this said, it will now imply that the availability of this lone pair is what determines the basicity. If you have a lone pair and that lone pair is available, it automatically means that you would have a high chance of being a base. With that said, basicity is simply a measure of the ease of donating the electron pair, which means the more the ease of donation, the higher its basicity. Now, for amines, which is the major thing we are considering, there are things that can affect the ease of donation. And the two major things that affect the ease of donation is what we refer to as the electronic effect and the solvation effect. The electronic effect is considered when the amines are in gaseous state, while the solvation effect is considered when the amines are dissolved in water. So which means anytime you are considering basicity, you must have in mind that if you are considering basicity of amines, is it dissolved in water or is it in gaseous state? When it is in gaseous state, electronic effect takes precedence. Considering electronic effect is basically the ability of a particular substance to release the electron pairs. So when you are considering the ability to shift or push away the electron pairs, that is what we refer to as the electronic effect. And we found out, or it is discovered, that once you have more electrons surrounding the particular atom possessing the lone pair of electrons, it automatically makes that particular substance to be more basic. What do I mean by that? Let's consider the three classes of amines, for instance, starting with the tertiary: nitrogen attached to alkyl, nitrogen attached to alkyl, nitrogen attached to alkyl. As I said, so it is believed that once you have electron releasing groups surrounding that particular atom, it increases the basicity. And very good examples, when I say electron releasing groups are less electronegative groups. So when I say electron releasing groups, they are less electronegative groups. Now, a very good example of a less electronegative group is the alkyl group. So have that in mind. Now, when you are dealing with the alkyl groups, automatically you would find out that the alkyl groups are less electronegative, and because they are less electronegative, they are electron releasing groups. These electron releasing groups, once they surround, the more you have electron releasing group, the higher the basicity. So the compound with the most electron releasing group is the tertiary amine. Hence, tertiary amine will be the most basic when you are considering the electronic effect. And I said that this electronic effect takes precedence when these things are in gaseous state, which means you don't consider this electronic effect when it is dissolved in water. As I say, take it again, electronic effect is only considered as a parameter for determining the strength of basicity when the substances are in gaseous state. And in this state, as I said, when you have more electron releasing groups surrounding a particular nitrogen atom, it increases its basicity. So that's why this particular tertiary amine would have more basicity than a secondary amine. A secondary amine should have R, R, and then H, lone pair. It has lesser electron releasing group than the tertiary amine, hence it should have less basicity. And then you have the primary amine, which should have the least number of electron releasing groups, okay, and hence it should have the least basicity. Now the primary amine has more basicity than ammonia, because ammonia does not have any of these electron releasing group. So automatically you have that the order is basically like this. Having said this, that is what we consider in electronic effect. In electronic effect, tertiary amines are more basic than secondary amines, and secondary amines are more basic than primary amines, which are more basic than ammonia. It simply means that these ones would easily give their electron pair or donate their electron pair than these ones, and these ones would easily or readily give the electron pair than this one. So have that in mind that it is dependent on the number of alkyl groups. So the more the alkyl groups surrounding the nitrogen, the higher its basicity. That's basically the principle. But that is when you are considering electronic effect, and electronic effect is considered only when the amines are in gaseous state. So you will notice that most of the times when you are considering amines, they are not always considered in gaseous state. They are either dissolved in water or in their liquid state. So the implication is that electronic effect is not a major parameter to determine the basicity of an amine. So let's consider what is required, or what is a major parameter in the basicity of an amine. That is what we refer to as the solvation effect. So when you say solvation effect, is basically the ability to form stable solutions as a result of interaction between the solute and the solvent. And solvation effect is most times considered when the substance is dissolved in water. So as I said, solvation effect is the effect of the interaction between the solute and the solvent to bring stability of the solution. So solvation effect is considered majorly in aqueous solutions. So when amines are dissolved in water, or basically when amines are dissolved, basically. So you have that once amines are dissolved, what you're going to consider is solvation effect. Now the thing about solvation effect is this: just as in electronic effect, the more the alkyl groups, the higher the solvation effect. But in the case of tertiary amines have more alkyl groups, and that alkyl group crowding actually leads to what we call a steric hindrance. A steric hindrance. Now, a steric hindrance is basically more like an obstruction to the rate of reactivity of a substance as a result of crowding. Originally, Ta or tertiary amines should be greater than secondary amines, but as a result of steric hindrance, which is caused by overcrowding, reduces basicity in a solution. So once you have that they are inside a particular solvent, steric hindrance can now have effect. As I said, steric hindrance is more like an effect as a result of overcrowding, which leads to the reduction in the rate of that particular reaction occurring. So originally, tertiary should be greater than secondary amines in basicity, but because of the fact that steric hindrance is considered when it is dissolved in water, automatically you have that secondary amines will now be more basic or greater in basicity than tertiary amines. So have that in mind. Secondary amines are greater in basicity than tertiary amines, which in turn are greater in basicity than primary amines, which in turn are greater in basicity than ammonia. And you have that when you are dealing with amines in solution, secondary amines have the highest basicity, while the lowest basicity is for ammonia. I hope this is easily understood. So we have that the order is going to be, when you are considering your electronic effect, tertiary amines greater than secondary amines greater than primary amines greater than ammonia. But in the case of your solvation effect, which is when the amines or ammonia are dissolved in water, you have that secondary amines are greater than tertiary amines, and the reason for that is because of the steric hindrance caused by overcrowding. Once they are dissolved in water as a result of the steric hindrance caused by overcrowding, you find out that the tertiary amines will form less stable alkyl ammonium ions than the secondary amines. So hindrance. Okay, so you have that. Now, secondary amines are more basic than tertiary amines, and these tertiary amines are more basic than the primary amines, and the primary amines are more basic than ammonia. And that's that basically about the levels of basicity. Now, we did not include or discuss the aryl amines in this case. and I would like to talk about that. First of all, is an aryl amine is basically an amine that is formed by attaching amine group to the benzene ring. And when you have a benzene ring attached to amine, this is what we refer to as aniline. The implication is that if it happens to form a carbocation by attaching itself to a hydrogen cation, automatically it is going to be referred to as an anilinium, basically. Now, the anilinium is okay. Okay. Now, basically, the aniline have this characteristic feature of delocalized electron pair. When I say delocalized, it means that the electron pair constantly moves from one place to another. And because the electron pair is delocalized, automatically it will not be readily available. Remember, we said initially that basicity is measured by availability of electron pair. So which means if the electron pair is not going to be available, the basicity is going to be low. That's what is happening in this case. So in aniline, the electron pair, because of the whole resonance occurring in this structure, will be delocalized and constantly be changing its location. Because of that constant change in its location, the basicity of aniline will become low. Hence, if you are going to consider the order in a solvation mixture or in an aqueous solution, in an aqueous solution, in an aqueous solution, in an aqueous solution, you will have that secondary amines would have higher basicity than tertiary amines, which will have higher basicity than primary amines, which will have higher basicity than ammonia. And because the electron pair in aniline is least readily available, it's always moving around, so it's not available for the bonding. So automatically you have that the unavailability of this electron pair as a result of its constant motion, its delocalization, will make it the least basic compound. So when you're looking at the strongest basic compound in an aqueous solution of basic amine, you have the secondary amine, while the least basic amine in a particular aqueous solution is the aniline. As I said, the reason for this is simple. Why is it that we have that? So aryl amines are generally less basic than alkyl amines because the nitrogen lone pair electrons are delocalized by interaction with aromatic ring pi electron system, which makes the electrons less available. Okay, so we've described why anilines have less basicity. It's simply because their electrons are less available. Having said that, let's consider these key points for determining basicity in amines. The first point is that basicity increases with an increasing negative charge on nitrogen. So if we are to consider nitrogen, for instance, when you have NH3 is neutral, but when you have NHH without any bond at this point, it is -1. In this case, an alkyl group can replace this, which means this is primary. I told you primary amines have 2 hydrogen. In the case where it now has 1 hydrogen, it becomes -2, and the bonds can be formed here. This is secondary amine, and then you have finally -3. This is tertiary amine. So as the negative charge increases in their gaseous state, that is when you are dealing with them in gaseous state, as the negative charges of their gaseous state ions increases, automatically what happens is that the basicity increases. That is why tertiary amines have the greatest basicity in gaseous state, while primary amines have the least, or ammonia in this case has the least. So in gaseous state, tertiary amines are greater than secondary amines, which are greater than primary amines, which are greater than ammonia itself, basically. But that is in gaseous state. Okay, we go to the next key point. Next point in this particular analysis is that inductive effect, that is to say, nearby, we talked about electronic effect. Electronic effects is the effect as a result of the presence of electron releasing groups or less electronegative groups. So when you have more electron releasing group, you have that automatically it increases the basicity. But in the case of inductive effect, it's the opposite. When you have more electron withdrawing groups, it reduces the basicity. And those electron withdrawing groups are the more electronegative groups. So that's that basically. So which means if, for instance, I have a particular amine, let's say I have something like aniline. Let's say I have aniline. If you attach an electron withdrawing group such as nitrogen, electron withdrawing group are more electronegative. Hence, they reduce basicity. So have that in mind, that once you have an electron withdrawing group attached to a particular distance, it reduces the basicity. So between nitroaniline, I meant to say, and methylamine. So between nitroaniline and methylamine, you will find out that methylamine would have more basicity. Why will it have more basicity? Because it has an electron releasing group instead of an electron withdrawing group. So which means that if you have an electron releasing group which are less electronegative, the basicity increases. So just have that in mind as the second point of that particular concept. Okay, moving ahead to the next key point. The third key point is that the basicity of NH2 will decrease if it is next to a pi acceptor such as C double bond O. A pi acceptor is basically an sp2 hybridized carbon atom. Let's call that an sp2 hybridized carbon atom. So when an amine group is attached to an sp2 hybridized carbon atom, automatically the amine's basicity would reduce. That is exactly why amides are less basic than amines. So you have that once amine is attached to an sp2 hybridized carbon atom, for instance, you have that C double bond O is attached to NH2. This is an sp2 hybridized carbon atom. We've discussed hybridization. Look up the study. Once you attach an amine to an sp2 hybridized carbon atom, it becomes less basic. Okay, but when you have this CH3 and is attached to an sp3 hybridized carbon atom, for instance, in this case, automatically this becomes more basic. This can actually also apply to the benzene ring, because the benzene ring basically contains 6 carbon atoms with sp2 hybridization. So when you attach an amine group to any of these carbon atoms, automatically it leads to a lowering of its basicity. So lower basicity. And what reduces basicity? Attachment of an amine group to an sp2 hybridized carbon atom. Okay, having said that, we go to the final point. So we'll go to the final point in our trends of basicity in amines. And the final point is that the basicity of nitrogen is highest for sp3 hybridized nitrogen. What is an sp3 hybridized nitrogen? It is simply a nitrogen atom that only has single bonds, which means that the sp2 would have double bonds, while the sp would have triple bonds. So I said the basicity of nitrogen is highest for sp3 hybridized nitrogen. I take it again. sp3 hybridized nitrogen is nitrogen with only single bonds. Let me put that on the screen so that we all can see it. So I take it again. sp3 hybridized hybridized nitrogen only has single bonds, which means sp2 hybridized nitrogen has double bonds, which means sp hybridized nitrogen would has triple bonds. Okay, so what does this actually mean? Consider when nitrogen is attached singly to alkyl groups or hydrogen and all whatnot, it would have the highest basicity. But if, for instance, I consider something like an enamine, an enamine is basically when nitrogen forms a double bond with a compound. So it could be nitrogen forming a double bond with carbon or something like that. That's an enamine. If you have this, it is more like lower basicity, which means when nitrogen now forms triple bond with carbon or with anything, in the case of nitrile, because it is sp hybridized, it would have the lowest basicity. So single bond, nitrogen forming single bonds all around, highest basicity, nitrogen forming double bond lower than this, and then the ones with the lowest are the ones that have nitrogen and triple bonds basically. So that's that about the basicity of nitrogen. So if I'm to put out a question and I say arrange these compounds in the order of their basicity, that is increasing basicity, that is from the lowest to the highest basicity, we would see that. So the compounds include A. Let's say we have something like CH3 attached to N. We have B, aniline, for instance. And then we have C, nitroaniline. So you will find out that, I said, from lowest to the highest. The one with the lowest basicity obviously has to be C. The two of them are both aryl amines. But I said that once you have an electron withdrawing group attached to aniline, it reduces the basicity. So this is the lowest. So we'll start with C, which will have a lower basicity than aniline. B, which will definitely have a lower basicity than your trimethyl amine, which is A in this case. And that's that basically about that, which is definitely have a lower basicity than A, which is your trimethyl amine. Why? Because if these things are all in their gaseous states, automatically tertiary amine would have the highest possible basicity. But even if it is dissolved in solution, when it is dissolved in a particular solvent, the only amine that has a higher basicity than tertiary amine in an aqueous solution is the secondary amine, and this is not found here. So you find out that your answer is the highest is A, followed by B, and followed by C.